I want you to picture the internet for a second. Close your eyes if you have to. Just visualize it. It is this absolute roaring ocean of voices. Everyone, and I mean everyone, has an opinion on everything.
It really is a sea of data.
Exactly. It's endless. You've got people ranting about, I don't know, a new French restaurant, debating the latest political scandal, reviewing a toaster oven like it's a piece of high art. It is the single most massive repository of human thought in history. But here's the problem. It's just, it's too much. It's chaos.
It is. If you're a human being trying to navigate that ocean alone, you're going to drown. You simply can't read it all.
Right.
The sheer volume makes it impossible for any single person to process. It's unstructured, it's messy, and a lot of it is, frankly, just noise.
Right. So how do we turn that noise into something useful? That's the mission we're on today. We're looking at a fascinating field called opinion mining and sentiment analysis. Basically, how do we teach computers to read all those millions of comments and tell us what the world is actually thinking?
And not just what they're thinking, but how they're feeling. It's about transforming that chaotic ocean of text into structured, actionable insights.
And it's not just for, tech companies or influencers.
No, not at all. The list of people who need this is surprisingly long.
I was going to say, obviously you have vendors. If you're selling a digital camera, you want to know if people hate the lens cap before you ship 1 million units.
Of course. But it goes deeper. Consumers need it to navigate peer evaluations so they don't buy a lemon. But think about citizens and governments.
Okay.
Citizens can use this to analyze politicians and policies, cutting through the spin to see what constituents actually feel.
And on the flip side, governments use this to monitor opinions expressed by what the source calls hostile entities.
Right.
Which sounds a little ominous, like straight out of a spy novel, but you can see the utility. If you can track the sentiment of a population in real time, that is powerful intelligence.
It is incredibly high stakes.
Yeah.
And what's fascinating here is that this technology represents a major shift in how we approach natural language processing, or NLP.
Yeah, let's do a quick history lesson here, because for a long time, computers were just fact checkers, weren't they? They were like glorified calculators for words.
Essentially, yes. Up until, say, the mid to late 1990s, NLP was obsessed with factual information extraction.
Just the facts.
Just the facts. The goal was to pull out dates, names, locations. Who did what to whom? If you fed a computer a sentence like, the election was held on Tuesday, it loved it.
It could handle that.
It could extract the date, the event. But if you said the election was a complete disaster, the computer would just
stare at you blankly.
Exactly. It couldn't process the subjective nature of the statement. But then researchers like Wiebe, Bruce, Hatzivasaloglu, and McKeown started asking a different question. They moved from extracting facts to extracting opinionated information.
So they stopped asking what happened and started asking, how do people feel about what happened?
Precisely. And that shift changed everything. It moved us from information retrieval to subjectivity analysis.
Okay, so before we get into the nuts and bolts of how a machine actually learns to understand sarcasm or joy, we need to clear up the jargon.
Good idea.
Because I feel like people use these terms interchangeably. Sentiment analysis, opinion mining, subjectivity, and the source material makes a real point to separate them. Let's unpack this.
It's important to distinguish them because they're actually different stages in the pipeline. Let's start with subjectivity analysis. This is about identifying what researchers call private states.
Private states? That sounds intriguing.
It's actually quite poetic. A private state is a thought, an emotion, or a belief that isn't objectively visible to the outside world.
Okay.
If I say the car is red, that's objective. I can see it, you can see it. But if I say international officers believe the EU will prevail, that reveals a mental state.
Okay. So the computer first has to figure out, is this a fact or is this happening inside someone's head?
Exactly. That is step one. The system has to distinguish between objective data and subjective expression. Then you have sentiment analysis. This is where we determine the valence. Is that private state positive or negative?
This is the thumbs up, thumbs down part.
It can be binary, like thumbs up or down.
Yeah.
But it can also be ordinal. Think of a 5-star rating system.
Sure.
And it applies to everything from single words, distinguishing hopeful from insipid, to entire documents, like a movie review.
So subjectivity is this an opinion? And sentiment is it a good or bad opinion?
You've got it. And then, at the highest level, you have opinion mining. This is the corpus level task.
Okay, the big picture.
The big picture. This is when you canvass all available sources to create a coherent summary. So instead of looking at one review, you're looking at 10,000 reviews for a digital camera to tell the vendor exactly where they stand in the market.
So it's the difference between reading a single tweet and understanding the mood of the entire country.
Ideally, yes. That is the ultimate goal.
Okay, so we know what we're trying to build. The source describes this idealized, unified system. I love that phrasing. It's like the holy grail of opinion mining.
It is.
Let's walk through how this system actually works step by step, because it starts with something that seems simple but is actually really hard: the dictionary.
We call it the lexicon. If you want a computer to know if a sentence is positive or negative, it first needs to know which words are positive or negative.
Right. It needs to know that excellent is good and atrocious is bad. But how do you teach it that? Do you just hand it a Webster's dictionary and a red pen?
Well, there are two ways. The manual method is exactly what it sounds like. You get a bunch of humans linguists, usually, to sit down and make lists.
Oh, wow.
They tag words as positive, negative, or neutral.
Which sounds exhausting and probably impossible to keep up to date. Slang changes every week. Sick used to mean ill, now it means cool. A manual list would be obsolete in a month.
Exactly. It offers high precision.
Yeah.
Humans understand nuance, but it has very low coverage. You can't list every evolving phrase manually. That's why the automatic method is where it gets really interesting.
This is the cool math part the source talks about. This blew my mind. You're saying you can teach a computer to build its own dictionary using just 2 words.
Just 2. This is the approach proposed by Turney and Littman. You start with seed words. Usually you take excellent for positive and poor for negative. That's it. You give the computer nothing else.
You just drop those 2 words into the ocean of text. Then what happens?
Then you use the statistical measure called PMI pointwise mutual information. Essentially, the computer analyzes a massive amount of text, say the entire internet, and looks at who hangs out with whom.
Like social circles in a high school cafeteria.
That is a perfect analogy. The theory is that positive words tend to appear near other positive words and negative words near negative words.
Okay.
So if a new word appears frequently near the word excellent, the computer infers that this new word is likely positive. If it appears often near poor, it's likely negative.
So if I say, the scenery was breathtaking and excellent, the computer sees breathtaking next to excellent and goes, aha, breathtaking must be a good word.
Exactly. It calculates the statistical probability of co-occurrence. This allows the system to learn thousands of sentiment words without a human ever having to label them.
It learns by association.
It builds a massive web of meaning just by watching how words interact.
That is incredibly smart. Okay, so step 1, we have our dictionary. The computer knows the words. Now, step 2, finding the opinions.
Right.
Because if I type digital camera into a standard search engine, I get Wikipedia pages, manuals, sales listings. Those aren't opinions.
Right. This is the retrieval challenge. It is not enough to find documents about the topic.
Yeah.
We need documents that express an opinion on the topic.
We need the reviews, the rants, the blog posts.
So the system performs a filter. It might do a standard search first to get the topic, but then it analyzes the results of those private state markers we talked about. It pushes the factual encyclopedias to the bottom and brings the subjective emotional text to the top.
Okay, so we have the words and we have the right documents, but here's where it gets messy. Because human beings are complicated. We rarely just say, this car is good. We say, the seats are comfy, but the steering wheel is weird and the gas mileage is, okay.
This is the facets problem. A blanket thumbs up or thumbs down is rarely useful for a detailed analysis. If you're the manufacturer, you need to know why the review is 3 stars.
And the source calls these specific things facets.
A facet is a component or attribute. In your car example, the seats are a facet. The steering wheel is a facet. The system has to identify these specific noun phrases to understand that the positive sentiment applies to the seats, but the negative sentiment applies to the steering wheel.
How does it know which nouns are facets? Because a review might mention my dog jumped in the car. Dog is a noun, but it's not a facet of the car.
It looks for frequency and modification. In camera reviews, the word lens appears constantly. The system picks up on that pattern, but then it has to prune the list. It checks if those nouns are actually being modified by opinion words. If people keep saying great lens, bad lens, fuzzy lens, the system confirms that lens is a facet worth tracking. It learns the structure of the object being reviewed.
But wait, context is huge here. The source brings up the word small. If I say, this hotel room is small, that's bad.
Definitely negative.
But if I say, this appliance has a small carbon footprint, or this camera is small and portable, that is good.
Precisely. This is the context challenge. A simple list of good words and bad words fails here because small is ambiguous.
Right.
The system has to understand the specific domain it is operating in. It has to know that in the domain of hotels, small is negative, but in ecology or electronics, small can be positive.
It's amazing how much cultural knowledge is embedded in that. The computer essentially has to learn the rules of the road for different industries.
It does, and it also has to figure out who is talking. This is the opinion holding.
I loved the example the source gave here. It said a critique of Hillary Clinton means something very different coming from Barack Obama versus coming from Charlie Sheen.
It illustrates the point perfectly. The holder is the entity expressing the opinion. The system needs to value and categorize these differently depending on the source.
But it's tricky, right? Because sometimes the person writing the article isn't the one with the opinion.
That is the difference between direct and indirect holders. If a text says, Taiwan-born voters criticize the policy, the voters are the direct holders.
Okay, straightforward.
But if it says, international officers said U.S. officials want the EU to prevail, you have a nesting doll situation.
Officers said that officials want.
Exactly. Who actually holds the opinion about the EU prevailing? It's the U.S. officials, not the international officers reporting it.
But a dumb system might just see officers and prevail and link them together.
Right. Advanced systems have to use sequence tagging to parse that grammar. They have to understand that the officers are just the messengers, and the officials are the ones with the private state. It shows you how complex the grammar can get.
Speaking of complex grammar, let's talk about the math of language, the advanced mechanics section. Because words don't just sit next to each other, they interact. The source talks about compositional semantics.
This is my favorite part. The sum of parts idea. You can't just add up the score of words.
Right. If I say war, that's a negative word.
Highly negative.
But if I say prevent war, I haven't made it double negative. I've made it positive.
That is the flip. The word prevent acts as a function that reverses the polarity of the word following it. The system has to understand that logical operation. It's not just 1 + 1.
It's an operator,
Yeah.
and then you have multipliers. Delicious is good. Absolutely delicious is better.
Absolutely acts as an intensifier.
Yeah.
But here is where it gets really nuanced. Consider the phrase not perfect.
Okay, perfect is a 10-10. So not perfect should be a flip, right?
Yeah.
Like 0-10.
You would think so if you just applied a simple not equals flip rule. But not perfect doesn't mean terrible. It doesn't mean atrocious.
No, it usually just means it's okay, like a 7.
Exactly. It's a dampener. It shifts the score down from a 10 to maybe a 6 or a 7. It doesn't reverse it completely. Teaching a machine the difference between a hard flip like not good and a dampener like not perfect is incredibly sophisticated.
So how do modern systems handle that? Because that sounds like a nightmare of manual rules. You'd have to write a rule for every single adjective.
We have moved beyond manual rules for this. Now, we use recursive neural networks and deep learning. We treat words as vectors arrows in a multidimensional meaning space.
Meaning space. Okay, explain that like I'm 12.
Imagine a giant map. Every word has a coordinate. Words with similar meanings are close together. Good and excellent are neighbors. Bad is way on the other side of the map.
Okay, so meaning is geometry.
In a way, yes. When you use vectors, the computer can handle complex structures mathematically. It sees the vector for not and the vector for perfect and calculates where they land in that space when combined.
And it learns that not perfect lands somewhere in the middle.
Exactly, somewhere in the middle of the map, not at the terrible pole. It allows it to handle things like, I'm not incredibly impressed, without needing a human to explain the grammar.
Wow, that is wild. Okay, we've conquered English. We can tell if a hotel room is small or if a carbon footprint is small. But the web is global. What happens when we want to analyze opinions in Romanian or Chinese?
The language barrier is a significant hurdle. Building those resources, the lexicon, the annotated data, is expensive and time-consuming. You don't want to start from scratch for every language on Earth.
So what are the shortcuts? There have to be shortcuts.
There are 3 main strategies. Method A is to translate the dictionary. You take your English list of good and bad words and translate it into Romanian.
Simple enough, though you might lose some nuance. Blue means sad in English, but might just mean a color in another language.
Exactly. It's quick, but risky. Method B is to translate the text. You take all those Chinese blog posts, run them through a machine translator into English, and then analyze them using your English system.
That feels like the brute force method.
It is, but it's becoming more effective as translation AI improves. But method C is fascinating. It uses parallel text.
This is like the Rosetta Stone approach.
Yes. Imagine you have a document, say a UN report or a movie subtitle, that is translated into both English and Chinese. You know the content is the same.
Okay.
So if the English version uses positive language, the computer infers that the corresponding Chinese characters are also positive.
It teaches itself Chinese sentiment by cheating off the English test.
Effectively, yes. It aligns the texts and projects the sentiment labels from one language to the other. It bridges the gap without needing a human translator in the loop.
That is incredibly clever. So we have built this massive end-to-end system. We've got the dictionary, the retrieval, the facets, the context, the complex math, multiple languages.
Yeah.
What's the end game here? What does the user actually see?
The goal isn't just a database, it's a summary. Imagine a dashboard. You might see a graph showing Prime Minister Sergei Stanishev. And connected to him, you see a green line indicating a positive view on the topic EU accession.
So it takes all those millions of messy sentences and boils them down to, this guy likes this thing.
Exactly. It aggregates the polarities and intensities to give you a bird's-eye view of public opinion. It turns the noise into a signal.
It's impressive, but I have to ask, is there anything it can't do?
Well, the source leaves us with a provocative thought. We spend so much time teaching machines to recognize love and hate, excellent and poor.
Mm-hmm.
But the hardest thing for them to spot is neutrality.
The feeling of meh.
The absence of strong feeling. Determining neutral sentiment is notoriously difficult and underexplored. When we don't feel strongly, we don't use those flashy adjectives. We just state facts, or we use vague language.
That is so true. It's easy to spot a scream. It's hard to interpret a shrug.
Exactly. And the danger is that if the system can't hear the silence, it might overrepresent the screams. As we teach machines to understand our wildest emotions, the hardest thing for them to understand might be when we just don't care that much at all.
Which is deeply human, isn't it? We notice the extremes and forget the middle.
We do, and now our machines do too.
Well, on that note, we're going to wrap up this deep dive. Next time you type a review or tweet an opinion, just remember, there might be a very smart algorithm reading it, doing geometry with your words, and trying to figure out if you are happy, sad, or just neutral. Thanks for listening, everyone.